There's the notes. And where am I going? Oh, there we go. Here we are. There's the notes. Linear correlation and really regression. So I want to talk about this here for you guys. Okay, now you might say, what do you mean? Well, we're going to gather data based on two variables, X and Y. Okay? So there's going to be two values that you gather data on, an X variable and a Y variable. Since it's two, they say this is bivariate, two variables. Bivariate data. And you're going to have a sample size again of this, but it's two values for one data set there. So anyway, bivariate data. And the question we want to have is that, is there a relationship between the two? Specifically, is there a linear correlation, linear relationship? Do you guys know what linear relationship really means? In some sense, we really mean, is there like this direct relationship from algebra? That's a linear equation here. Can I describe this relationship with a line? Because the graph of a linear equation in algebra is a line. So we have this X variable, and you have a Y variable. The X variable, in theory, can be controlled. So this is called the independent variable, X. X is independent. It could be controlled. Y is called the dependent variable. Now, things like this, if you said, because there's a classical example that was on my website. I wish I didn't get rid of it. I did this morning, and I'm like, darn it, I really regret it. You know, I got rid of that sheet. Felt bad about it. But anyway, it's like the relationship between study time and the grade earned on a test. Study time and the grade earned. So the idea behind that example is if you studied more hours or more minutes, whatever, you would get a better grade. You guys understand what I'm saying? And points. So you have like study time versus the points you get. So in that example, it was on my website. I regret getting rid of it, but that's kind of a great example. Study time, so in theory, can be controlled. It's independent. And then what you get depends on, as a grade, the study time. So anyway, but that's the idea here behind this. Now, this goes back to one idea about data. What else I want to say? Yeah. Since it is actually what? An X and Y value here, ladies and gentlemen. There's a lot of formality to what we're going to do here. There's a lot under the hood, trust me. There's a lot of mathematics under the hood. Heavy-duty math is under this hood. But as you guys can see, we replace the heavy-duty math with what? With technology. And so you said to me, well, Mr. Judge, if we go back and talk a little bit about some algebra in this course, this X course, since we're going to gather data that's bivariate to two variables, here's kind of the idea behind it, okay? When you plot the data values on your Cartesian coordinate system, plot. Here's your bivariate data with two variables, X and Y. The question we're going to have is, can we describe, or does that data possibly fit on a straight line? So when we plot the sample data, sample size n still, will that data fit on a straight line? That line, if it does, like in this picture, we go, maybe. It looks like it kind of can fit it. This line is known as the best fit line. We can best fit our data on that line. That line comes from beginning algebra. That's y equals mx plus b. You guys ever see beginning algebra before with that line? Y is mx plus b? Well, it's kind of back. That's called the best fit line, but this is also known as the regression line. So a lot of times you might see this idea linked together. Linear correlation and regression, because it's based on, ladies and gentlemen, looking at the data and seeing if you can fit it on a line. Can that data be best fit on a line? And you say, well, why would I want to do that? So I could be predictive. If you know the equation that your data fits, you can now predict with some degree of accuracy. All right, you guys okay with that? All right, now here's but there is some formality, okay? There's a little bit of formality here to let you guys know, and there's a lot of math under the hood, and I have to debate how much of that I really want to go in and dive deep into, you know? Because I left a lot of that in my notes, so you guys know, for historical reasons. And then there's a very simple, the TI version of it. And the TI version, it simplifies everything. So the good news is there is a formal hypothesis test associated with all of this. There is, but it's kind of like a default test, like a template that you guys use. Just the template hypothesis testing. It's a two-tail test. So we have a template hypothesis testing. The formality of it, we'll go through it. But, you know, there's a lot of math under this hood. So n represents the number of pairs of data. That's your sample size. And then sigma is the summation symbol. And then, ladies and gentlemen, you see all of this? This was all under the hood back in the day. Some x, some y, some xy. This is all your data you gathered because it's bivariate, right? Remember this, your x coordinate, I'll put orange today. Y coordinate, I'll put green. And then sample size n right over here. And ladies and gentlemen, there's your bivariate data. And you're going to be familiar with this thing called R. R is kind of an informal measure, but it's the measure that approximates, I'll say, rho. You go, what in the world is rho? Well, remember this. Remember how you have a population and you can't ask everybody in the population, right? You're going to have to take a sample because you can't ask everyone. Well, rho is really a parameter. It's another parameter. It's the linear correlation coefficient for the population for paired data values if you were to take a census. So remember that idea. You can't take a census. Too expensive, too time consuming. So you end up taking a what? Sample. Rho is the linear correlation coefficient for paired sample data values. So this is kind of a formal and informal thing. Rho is really a measure of whether there is a linear correlation. You want to think of it that way. So is R. They're measures of where if there's a linear correlation. Okay? And so let's go through the requirements, the formal legalese requirements here. The linear coefficient can always be computed for any set of sampled bivariate pairs of data. but the following requirements should be satisfied when using sample pair of data. Number one, essentially this. The sample pair of data has to be random. Okay, well, that makes sense. We talked about that. It can't be convenient, nor can it be voluntary. A lot of surveys are bad because they're voluntary. And really the first step you want to do is to create what's called a scatter plot. You go, scatter plot? Yeah. Because what you want to do is you want to confirm that the points essentially what? Approximate a straight line pattern. Go, what? Yeah, like if I go back to this picture, what do you think this is a picture of, ladies and gentlemen? This is a picture of a scatter plot. Yeah, you guys ever see that before in your life? Anybody ever see this before in a statistics course, whether it's high school, middle school? Yeah. So you want to see, does your data approximate a line? Bivariate data. If it does, then you proceed. If it doesn't, you don't, because why bother? Does that make any sense? You can't be predictive if your data is random. All right. That's what they're saying in number 2. You do a visual approximation to see if it is a line. Hopefully it is. If it is, then you proceed. The results are strongly influenced by outliers. You guys want to know what's an outlier, by the way? What's an outlier? Well, not necessarily outside the sample. Like if I said to you guys, you know what? We got a data value out here. It's away from all the others. So if you have like a straggling data value, we call that an outlier. You can have more than one. It could be another one, like maybe somehow you gathered data and it was way out here. You go, oh, we got another outlier. Well, here's what you do with outliers. Essentially, you get rid of outliers, in all honesty. Now, some of that stuff can be debated. Do you get rid of the outliers? Do you keep the outliers? But for a scatter plot and for this topic, linear correlation, you probably want to get rid of outliers because why? Results are strongly influenced by outliers. This whole process is very sensitive to outliers, so you get rid of them. So they must be removed where they are known to be errors. If you know to be errors, yeah, you remove them. At times, we may calculate the linear correlation coefficient with or without the outliers when considering this. So they just kind of avoided the controversy. At times they may, at times they may not. Well, typically they throw out the outliers. Sometimes you keep them, sometimes you don't. It'll change things. But what you must have is this too. Formally, we require that both variables x and y have normal distribution, which is known as a bivariate normal distribution. This is very difficult to check, so we rely on requirements 2 and 3. So that is something that is not part of our formal process here in this course. Whether the x variable and y variable are normal, it goes way beyond. So like I said, a lot of the math here is pretty high, is pretty sophisticated. But technology replaces it. All right. Historically, this is what our students had to do when they computed that linear correlation coefficient. Think of it as this is kind of the R value that tells you everything to some degree. It really doesn't, but it tells you a lot. And notice historically, that was the formula. I taught this course earlier today. Those morning students fell out of their chair when they seen that. They go, oh! And actually, back in the day when we did this, yeah, people looked at that and said, oh, but they found that it was pretty easy to use. But anyway, we don't use this anymore. Instead, what do we use? You guys know what I say. What's coming? Yeah, you guys use a TI. All right, you guys okay with that? So don't worry about that part. You're going to use the TI. All right. Now, here's facts about R. R lives between two numbers, ladies and gentlemen. R I guess I'll use green today for R. Maybe. I don't know what I'll use. R is between -1 and 1. The closer you are to +1, the stronger the linear correlation. The closer you are to -1, the stronger the linear correlation. But there's two types. So R measures the strength of the linear relationship between the two variables. So let me put this in our notes so you guys know. R close to 1, we have a strong what? Positive linear correlation. R close to -1, you have a strong negative linear correlation. R close to 0, no linear correlation. So if R is close to 0, there's no linear correlation. That applies to rho just as much as R. R close to 1, a strong positive linear correlation. R close to -1, strong negative. But like always, what do they mean by the word what? Close to. What is close? That's kind of an issue. Being close. Anyway, thankfully we have a formal hypothesis test for this. Okay. So here's the details. Hypothesis test for rho. Here's what you guys always assume. This is the formal test. Okay. H0, rho equals 0. That means there's no linear correlation. That's your null hypothesis. Okay. H1, rho is not equal to 0. Your conclusion is there is a linear correlation. And by the way, this is always the claim, if you guys want to know formally. And this will always be, if it's not equal, what does that mean? Do you guys remember? What does that mean? A 2 what? Tail test. All right, you guys okay with that? This is the default template. It's like a template you use every time. But what I want to point out to you guys here is this as well. Linear correlation hypothesis test is either 1% or 5%. So you're going to always see that. You're going to see, how come they only have 1% or 5% and no 10%? Well, they don't use a 10% test. That's all. And it's going to be what distribution here? What does it say? You're going to use the t distribution. Now, if I say t distribution, you say, well, what does that look like in my decision rule? Well, let me ask you guys this question here. You need critical values, don't you? What have we learned about this? What do you guys know about the t-test? How do you always get your critical values with the t-test? Always, always, always. What do you guys use? Inverse what? What did you learn last time? What function do you use for the t? for critical values? We always use inverse what? T. What do you use for the Z distribution? Inverse norm. It's normal distribution, Z distribution. Critical values for a Z distribution, inverse norm. Critical values for a T, inverse T. But remember, inverse T has some particular things. What did we see last time? You need area to the left of the rightmost critical value. Do you guys remember that? We worked on that last time. Area to the left of the rightmost. Just want to remind you guys, okay? And then what I have to say that's new, you see the degree of freedom? What's your degree of freedom now? It's n minus 2. N minus 2. So for linear correlation, the degree of freedom is not n minus 1. It is what? N minus 2. There's a lot of math under the hood here, ladies and gentlemen. There's a lot of math. So you go, where does that even come from? It goes way beyond the scope. But I want you guys to know this area to the left, and now your degree of freedom is n minus 2. This is how you get critical values for linear correlation hypothesis test. This is the default setup. Always, always, always. That's your default setup. Rho equals 0, no linear correlation. Rho is not 0, there is a linear correlation. It is always a two-tailed test here. You do have a test statistic, but like I said, this is the old formula. We don't use this. We use the what? The TI calculator. So you, in the old days, you computed R, and then you computed the test statistic. In the old days. Not anymore. What do you guys do? TI. So in some ways, I just have to show you guys how to do this on the TI. And it's not that hard. Yes. Are there some steps? Yes. Did I print up the steps for you? Yes. How do you get good? You practice the steps, and then you could do it in your sleep. That's how it works. But you got to practice. But if you don't practice, it's not going to be there. You guys know what I mean? It just isn't. Okay. There we go. You guys ready to see the steps? All right. Now, I want to give you guys a little story here so you guys know, right? Here's your first example. This is how it works. They want to know, is there a relationship, meaning a linear relationship, between the weight of cars and fuel consumption? What do they mean by the weight of cars? Cars in pounds, fuel consumption in mpg. Do you guys know what that means? What does that mean? What is mpg? Miles per what? Gallon. So how many miles you get per gallon? So here's what they're saying. The bivariate data listed below are the weights in pounds and the highway fuel consumption in mpg of randomly selected cars. Is there a linear relationship between the weight and highway fuel consumption using alpha being what? 5%. So let's look at this. Remember I said your data is bivariate, two variables? So you have x versus y in algebra, which is really weight versus fuel consumption here. So I'm going to color coordinate this This X, the weight, which is right in here. These are all the weights. Fuel consumption is Y. Here's your fuel consumption. So here's what that means. When a car weighs 3,175 pounds, what's the fuel consumption? 27 miles per gallon. When the car weighs 3,450 pounds, what's the fuel consumption? 29 miles per gallon. If it weighs 3,225 pounds, what's the fuel consumption? 27 miles per gallon. 3,985 pounds, what's your fuel consumption? 24 miles per gallon. When it weighs 2,440 pounds, the fuel consumption is 37 miles per gallon. When it weighs 2,500 pounds, the fuel consumption is 34 miles per gallon. And then finally, when it's 2,290 pounds, fuel consumption is 37 miles per gallon. So they want to know, is there a linear relationship between the two? Okay. This is our bivariate data. Now, what you guys really want to do first is know, okay, this is the X coordinate, this is the Y coordinate. You're going to create a scatter plot of the data. Okay, now, that's the first step. They say, okay, create the scatter plot. See if there is a straight line pattern and determine if there's any outliers that can be removed. So this is my data of weight down here. This is the weight, the x-axis, and the y-axis from algebra. We plotted those points. Can you describe the data possibly? Is that in the straight line pattern? What do you guys think? Is there a straight line pattern here for the data? What'd you guys say? I say there is. Can I kind of fit that data with a straight line possibly? You guys know what I mean? Maybe kind of fit that data? Is there in a straight line pattern? The answer is what? Possibly yes. It's not perfect, but it seems like the data is in the form of a straight line. So if I can find that best fit line, called the regression line, I could be predictive, and that's what I'm looking for. This is what this is all about. So far, with the scatter plot, it does look like we should proceed. Scatter plot. We're going to proceed. What do you guys think? All right. Now, get out your template. What's the template? H naught is rho equals 0. There is no linear correlation. Okay. H1, rho is not 0. There is a linear correlation. So you set this up. This is a two-tailed test. We already went through that. But in this test, alpha is what? 5%. So if there's two tails, 2.5% is in each tail. Is that right? So you guys have done this before. The question is, how now do they get these what? These critical values? Well, very simply. What do we use? Inverse what? T. This is a T distribution. You're going to use inverse T here. But remember, inverse T wants the area to the left of the rightmost critical value. So if alpha is 5%, what percent is right in here? Do you guys know? Isn't that the complement, which is 95%? So area to the left of the rightmost critical value, remember we got to enter that. Isn't that going to be 97.5%? Because 5% plus 2.5, isn't that 97.5%? Right? You guys with me on that? You guys see that there? It's 97.5%. This is how you always use inverse t for two tails. But how many data values were in the sample? Do you guys remember? We didn't even count. How many? 1, 2, 3, 4, 5, 6, 7. What does that mean about my degree of freedom if there's 7 data values? This is only for linear correlation. 7 minus 2 is what? What's 7 minus 2? Isn't that 5? So your degree of freedom here is 5. So what we're doing here is we're looking at the information we need and how to get those critical values, inverse t. Okay. Second distribution, inverse t here, right? Oh, it's already on 0.975. Good. The degree of freedom was what? Was it 5? Okay, what do we do with that? Paste it in. If we go to the nearest thousandths in this example, isn't it 2.571? Inverse t, ladies and gentlemen. So this is how they got the critical values. Okay, so I'm going to erase this here. Since we went through how they got the critical values, they're using inverse t because, again, isn't this the what? T distribution? See there, t distribution and what? Inverse t. That's how you know. Z distribution is inverse norm. Those programmers, they were not really consistent when they did this. That's what bothers me. Okay, so this is your formal default hypothesis test, but how you end up getting your critical values is done this way. So you got to follow that process, that procedure, okay? That's step 2. So in the old days, we had to do all this. We had to compute R. We don't have to do this anymore. And once they got their R value, then they computed their T value. That's the test statistic in the old days. So ladies and gentlemen, yeah, this is T, this is R. From the old days, you needed the R value to get the T value back in those days. And notice that R value is pretty close to -1. Isn't that right? That should give you a tip-off already informally that looks like there'll be a negative linear correlation. And negative just means it's a downhill slope for the line. So just looking at this from the old days, all that information, I'm keeping it from the old days just for historical purposes in the notes. Don't let it scare you, because guess what? All you have to do is follow this procedure. So now I'm going to focus on what you guys do. So at this point, I laid the foundation. What we're doing, why, where it comes from, what this means. I set the table here for you. Now we have to get down to the nitty-gritty. You know what we got to do? We got to enter our data so we can make a scatter plot. How do you guys enter data? You're used to entering data into one variable, AL1. See that here? This is all in orange, AL1. This is in green, AL2. This, AL1, is where I put my X variable information. AL2 is the Y variable. So you have what? The X, and we have the what? The Y. So how you enter data is how you've been entering data from that first week. I'm not going to go back to that worksheet here online and show you guys. I'm going to show you guys in the TI. We got to go, remember this? We're going to enter those data values. We're going to go to stat, edit, edit. You see this here? I got to clear this out. This is clear. I got to clear this out. Clear. In L1, I enter the X values. In L2, I enter the what? The Y values. You guys okay with that? We got to enter the data, and we're going to create a scatter plot. And you say, where do I get the data now? From the problem. Your X variable, your Y variable. Right in here. So let's enter all the orange values in L1 and the green values in L2. So you're going to have to enter data in your calculator. So, okay. So 3,175. 3,450. That's the second value. You guys okay with that? 3,225. Okay. 3,985. All right. 2,440. Okay. 2,500. All right. 2,200 and what? 90. These are all the X values, okay? Do you guys see that there? I entered all the orange values in L1. L2 is all the Y values. All right. So let's go to the Y values now. What's the first Y value? 27. What's the next one? 29. What's the third one? 27. And then 24. And then 37. And then 34. And then again, another 37, ladies and gentlemen. So this is what it looks like to enter the bivariate data here. You entered bivariate, two variables here. Okay? So in my notes, if I go back to the iPad, you go, oh, did you put this in the notes? Yes, I did. It's right over here. So if you guys have to go back and watch the video or look at the instructions about entering bivariate data for the purpose of creating a scatter plot, right? That's what you do. All right. Anybody have any questions on that? No, it's even in the notes here. You're going to buy these notes at Barnes & Noble? I don't know. Put them on offer up, maybe? Print them up. All right. Now, this is how we create a scatter plot. That's always your first step. So in your notes, you're going to follow this set of instructions to create that scatter plot. Now you say, how do I do that? The scatter plot is found doing this way. You're going to have to go to open the stat. You go open stats plots menu, and you go, how do I get to the stat plots menu? Right? How do I get there? You do what? You press the second Y key. You go, what? Right in here. See this right here? The second gets you in the blue mode. Why do you guys want to go in the blue mode? Because isn't that where stat plot is? So, let's see. All right, maybe we got to, should we scroll in? I don't know. Let's take a look. Second, there we are. So you're in stat plots. That's what it says on top. So in your instructions now, you go, how do I do that? Well, what does it say? it says press enter to do what? Press enter to access plot 1 settings. Okay. Enter. Notice we have to go to the plot 1 settings. Now, in the instructions, they want you to do what in the instructions here? Right? Oh, let me go back. I don't think I showed you guys that. So, seconds plot. Let's go back here. Press enter. You're in this one. Press enter. Okay, what do the notes say? Select what? On and press enter. Select on. Yes, you see this here? It's on. Select enter. Make sure that's on. It could be off. It could be on. All you want to do is make sure it's on. And then scroll down to that first type. You say, why? Okay, let me go back here. Here's the calculator. Make sure you're on. Okay. Scroll down to that first type. That's a scatter plot right there. So you put it on, you put scatter plot. Now notice here in the calculator, you got L1, you got L2. So it's supposed to look like this. On scatter plot. The first one's a scatter plot. Oh. All right, let's see what we do now. You guys ready? What do we do now? Here's what I'm going to say. Select the first chart option, scatter plot, and then press enter. We did. This is what we did. And yes, this is the names L1 and L2. But now I want you guys to do this. What do? You press zoom, then 9, zoom stat. Zoom, and then 9, zoom stat. All righty. What does that mean? Here's what that means, ladies and gentlemen. Let me go back over here to let you guys know in the notes. Zoom is right here. So once you hit zoom and you're in that zoom, you're going to select zoom stat, number 9. I don't know why. They should have just called that scatter plot. I really know why they did that. If I had to design this, it would be very different. All right, here we go. Zoom, scroll down to 9, called zoom stat, and there's your scatter plot, ladies and gentlemen. So it's that procedure you want to follow to create a what? Scatter plot. So if I were you, I'd follow that procedure, and then I'd look at this. This is all my data. And does that look like your data is in line, by the way? Say yes. Looks like the data follows a line with a negative slope. So your data does find a line kind of pattern. That's your scatter plot, ladies and gentlemen. And the instructions are here. And I even drew a picture. Here's my point. It looks like the data can be what? Fit. Not very well, but we can fit it in a line. And that line has a negative slope downhill. Remember your slope from beginning algebra? It's downhill. That's a negative slope. That y is mx plus b from beginning algebra. There's your line, ladies and gentlemen. So you're looking at these procedures to draw that line. So that's what I'm saying. This is what you should see in your scatter plot. Those are all in your notes. So what you want to do is practice that so you can draw a scatter plot and check to see if there's a line. All right. Great. Now what do I do? Oops. I don't know what I did. Somebody did a screenshot. I don't know what I did. Okay. All right. So you say, now what do I do? Well, now you're going to compute your test statistic, right? Remember that formula I said you don't have to find? So we're going to compute the test statistic, ladies and gentlemen. T, we're going to find the R value, the linear coefficient. R, we're even going to find a T value. I think my test statistic I've always done purple. We're going to get the P value. So you say, how do I do that? Well, you're going to go to stat test, linear regression t-test. So everything that we've been doing with hypothesis testing, we've been doing stat test, stat test, stat test. Now you go to stat test, linear regression t-test. So with all of that information here, you still go to stat test like you've been doing, but now where do you go? Linear regression t-test. It's all the way down here. Did you guys see that? It's F. F, linear regression t-test. F, linear regression t-test. So what you're saying here, make sure it's on L1, L2. Make sure it's on a two-tail test. That's two-tail. This is linear regression t-test. What do you think you hit? Calculate. Now, notice this information you get here. I can scroll down. There's a lot of information. Scroll up, scroll down, a lot of information here, ladies and gentlemen. And I have this even in the notes that when you went through the linear regression t-test right here, and you went through and labeled two-tail test, that's all you do. You got all the nice information. Now, do you guys remember where is the test statistic value? Right here. Wasn't the t-value the test statistic? So what's this test statistic going to be? It's negative 6.393. Okay, you guys see that there? Negative 6.393? All right. So you go, what do I do with that number? Go back to your decision rule. Where is negative 6.393 in the decision rule? I'm getting rid of this so it doesn't distract us. Well, it's negative, so it's to the left. Is it past the critical value? Say what? Yes. That t-value is past. It's further away from 0. It's past the critical value. What region is it in? It's in the what? Reject the null hypothesis region. Is that true? You are rejecting the what, ladies and gentlemen? You're rejecting the null. And when you reject the null, what does that mean to reject the null? Say goodbye, null. You're accepting the what? Alternate. What is the alternate again? The statement that there is a linear correlation. This is always the claim by default. You'll see that we don't say sample supports the claim, but it does because that's the claim. It's not written in the question like the others. It might be. But this says that there is a what? A linear correlation. So, ladies and gentlemen, you get your t-value. And this is what I have here. There it is. Yes, you reject the null. And what does that mean? there is a linear correlation. That's what you're doing. Now, I know when you see the first question, it takes some time because you go, oh my God, because you're learning a procedure, but this gets easier as you move on, as you get practice. You guys know what I mean? Just gets easier. The more you do, the easier it gets. You can do it in your sleep. But if you don't practice, then it doesn't happen, right? So I want you guys to also notice, what was the next value here? Do you guys remember? Remember we did this? We approximated. This is the p-value right here. So I'm going to say, here's my test statistic. Here's my what? P-value. If we go to the nearest penny, what is this? Isn't that by 0, 0? It's the nearest penny? So you notice what I have here in our summary, in our notes. Here's the p-value. What do we want the p-value to be less than? If the p-value is less than the level of significance of 5%, what do you guys automatically do? Right? It's right there. The p-value of 0, 0 is less than the level of significance. So you accept the alternate hypothesis. So if you go back to your template, this is the template of the hypothesis test. It's called template. Didn't you automatically accept the null? Which is the fact that there's a linear correlation here. That's the claim again. So ladies and gentlemen, what I'm suggesting to you is that it's consistent with the p-value as well. So just to kind of throw that out there, it's consistent. So now that you know this, you might say, but Mr. Judge, what's the deal with this R value of a negative 944? R is close to negative 1. So this R value is what? Close to negative 1. That's why I put R here. Now you say, where did I get the R value? What do you guys think the R value is? How do I know that this is the R value? Because it's right there. All that information is here. There's your R value. So linear regression t-test gives you all the information you need. It gets even better. What's the whole point of all this, ladies and gentlemen, again, once you know this? So there is a linear correlation. What do you want to do? What's this line called again? Once you know there's a linear correlation, what do you want? You want that line. What is that line called again? We said it. What's it called? The best fit what? Line. That's the line you could best fit your data in. This is also called the what? Regression line. How do you think we get the line? Well, yes, the line is y equals mx plus b. We don't go back to algebra. Do you guys know how we get the line? It's also in the what? It's in the TI calculator. You know what it is? They write it this way. Y is a plus bx. They don't put the m. It's a different b. Oh, algebra is no longer a prerequisite. We don't care about this equation anymore. Y equals a plus bx. That is the regression line formula. Okay, you guys okay with that? It's a linear equation from beginning algebra. Y is a plus bx. So now that you know the data fits on a line, best fits, sort of, how do we end up getting that regression line? Well, it's right here. What do I mean it's right here? A and B are right here. I'm going to say that again. A and B are right there. You guys see it? That's why they call it linear regression t-test. A and B are here. So A and B, you say, well, what is that? Well, I write this down this way. Y equals A plus B times a variable X. A, if I go to the thousands, what is A? Isn't that 54.695? Okay. There's the A value right here, 54.695. What is the B value to the thousands? So notice I'm going to the thousands for both of these. What's the B value? Negative 0.008? X. A value, B value. This is the equation that they're looking for, ladies and gentlemen. That's what they're looking for. Why do they want this equation? Do you guys know why they want it? So you can be predictive. So all you got to do is give me now an X value. I don't even know what color to use now. So if they say, what if X is, remember, X is the weight of a car. Oh, and I'm giving it here. Here's the best fit line. It's in my summary. Okay, Y is AB X. All right. There it is. I wrote it in a different order. Okay. There we go. It's in the summary as well. There. Okay. But here's what I want you guys to know. Now I'm gonna create a weight. What if the car weighs 2,500 pounds? That's an X value. So if your car weighs 2,500 pounds, what is Y? Because remember, X is the weight in pounds. Y is the fuel economy in MPG. So what you'll do is you plug in for X algebra. Oh, I know, there's no longer a prerequisite of algebra. Here we go. Let's find out what that is. This is what's replacing algebra, the calculator. 54.695 minus 0.008 times. Now comes the X value. What was the weight? 2,500. So what do you guys get here? What does this mean? That's the MPG. If I go to the nearest whole number now, because when you buy a car, right, they don't give the MPG in a decimal. They give a whole number MPG. So Y is approximately 35. This is what you're looking for. That's the fuel economy. 35 miles per what? Per gallon. That's what you're looking for. Yes. Oh, is there already 2,500 here? Yeah, that's okay. Good observation. Good observation. Yeah, slightly off, but that's why, because it's an approximation of a line that's best fitting. That's why they call it the best fit line. Anyway, you said, Mr. Judge, don't do that. Is there a 28? Is it 2,800 pounds? Thank you for being awake. You go, Mr. Judge, I want to do one like this. What if it's 2,800 pounds? They don't have that data for 2,800. Okay. Replace X with 2,800 then. Let's see what the MPG is. What is Y? So in your calculator again, we'll clear that out. We're going to put what? 54 point what? 695 minus 0.008 times the car weighs 2,800 pounds. Okay, go to the nearest whole number. What is this as a whole number? This is what? This is 32 what? Miles per gallon. That's completing the process. This is what they're looking for. If there's a linear correlation, what is the regression line? And then here's an example of why you care so you can be predictive. Easy peasy lemon squeezy? Sort of. When you see the first one, you go, that's a long process. But as you do more and more, it becomes quicker. You just have to get used to using the instructions on your what? On your TI. Okay. Here's what I did here. The next example has notes. In the next example, there are notes. In other words, but I didn't give a real what? What didn't I give? This is just a general X versus Y. They didn't give you a physical setting. So here they're saying, here is some bivariate data. Use the TI calculator with a 5% level of significance. There's my alpha. To test the claim that there is a linear correlation between the variables X and Y. Determine the test statistic and the linear coefficient R. So this is just some regular old data. X versus Y right in here. Okay, it's kind of an exercise. You could do that. A lot of books do. What they do is they say, okay, here's some X and Y values. They don't waste time trying to scare you with the physical setting, although I don't think that's very scary personally. But they want you to do the process here, enter L1 and L2. Okay? So there's the L1 and L2 values. So if you look closer, here's L1, here's what? L2. So I'm going to go through this to share this with you guys. Now notice though, we got to follow the procedure. So I'm going to go to my TI, and what am I going to do? I'm going to go to Stat, Edit. But do you guys remember? How do you clear this out? This was from the last problem. What do? You go up and hit what? Clear. Come back down. Everything in L2 is gone. Go to the left. Go up and hit what? Clear. Come back down. You guys okay with this? Now, enter the data values you have there. All the X values in L1, all the Y values in L2. Enter them. Like I said, you just got to practice using that TI. So 10, enter. 12, enter. 13.5. We can scroll down. We can put enter. You can say 15, enter. 16.5, enter. 18, enter. 20, enter. 21.5, enter. What else? 23. Okay, now go to L2 because you guys are going to practice this. Go to L2. First value is 25, enter. 28.2 and enter. 30.5, enter. 36, enter. 38, enter. 42.5, what else? 45. 48, and then what's the next one? 49.2. Okay? So we entered this data. So this is what I'm saying to you. Enter your bivariate data. And then after you enter the data, you're going to create the what? The scatter plot. Yes, you have to follow your procedure. It's not listed here. It's listed above the instructions. Okay? But these are the windows you guys should see in the instructions. So I summarized it here. So you go, oh, well, what do I do? Well, let me show you guys in the instructions if you guys forgot. You hit second and what? Scatter plot. Go to the first one, press enter. Make sure this is on. Make sure this is on scatter plot. Make sure that's on L1 and L2. And it is. Do you guys know what you do next? And it's in the instructions. Next, you go up here to zoom. Zoom. And which one do you go down to? Number 9, zoom stat. Okay, hit enter. What are you guys looking at? Is that the scatter plot, ladies and gentlemen? Wasn't it easier to do this time? It'll get easier and easier. There's your scatter plot, ladies and gentlemen. That's the line. Does it look like your data fits in a line? Yeah, it looks like your data is strongly in a positive line, positive slope. So, yeah, the scatter plot looks pretty good to me. All right. Okay. It was easier. There's a scatter plot. This is what you should see. This is what I'm sharing with you guys in the notes. So your notes correspond with the video. Looks like, here's what we're saying here, that, ladies and gentlemen, the data fits on a line. Notice the slope of that line is positive. That means it's a positive. And in fact, it looks like the data really fits on the line, doesn't it? So this is what we say. It looks like there's a strong what? Positive slope line. Linear correlation. That's what it looks like. What do you guys think? Is that okay? That's what we're saying. Now, at this point, they're going to want you to create a what? A formal hypothesis test over rho not equal to 0, claiming there is a linear correlation. Alpha here is 5%. The degree of freedom, they told us here, is 7. Now, why is that degree of freedom 7? Go back to your data values. How many pairs of bivariate do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So sure enough, 9 minus 2. This is only 4. Linear correlation. All the other degree of freedom, the t distribution is n minus 1. But for linear correlation, it's n minus 2. So this is what I summarized here in your notes. This is why it's 7. Now, when I enter this to get my critical values here, remember this is inverse t now. Aren't I supposed to put 0.975, area to the left or the right, most critical value, degree of freedom is 7, in that bow-shaped curve? Now, I'm going to go to the nearest hundredths here. Your critical value here, remember there's 2. It'll be plus or minus 2.3 what? 6. 2 of those. Inverse T gives us the critical values. So I need that because my template, the default, 3, 6. I noticed it. Oh, it is. Oh, that's the one. I'm sorry. This is supposed to be a 3, 6. Only have one. 2.36 minus 2.36. Oh, that was creepy when I seen it. I'm like, oh my God, I got to fix that. Here's your critical values. Rho equals 0. That's the null hypothesis. No linear correlation. Rho is not 0. Alternate claim. Remember, two-tail test. Just to kind of go through the details. This is always your hypothesis setup. And then here's your critical values you just found. Notice alpha is 5%. Sum of the tails is 2.5%. That's alpha. Is that consistent with what we did in the prior? This is your hypothesis setup always. Now you say, what do I do with this information now, Mr. Judge? You're going to go to what? Linear regression t-test. Okay? And this is what you're going to see, or this is how you do it, right? In your calculator, linear regression t-test. So we go now, stat, test, linear regression t-test. There it is. Make sure it's on L1 and L2. It will be. Don't change the frequency. Make sure it's on a two-tail test. Calculate. Ladies and gentlemen, if I scroll up and down, I could get all the data values I need because there's a lot of information here. Okay? I summarize that even in the notes. There's your notes. What am I looking for, ladies and gentlemen? What do I need? Again, where's your test statistic? Right here. What's your test statistic value to the nearest hundredths? Is T 21.74? Sure is. There's your test statistic. What do I do with 21.74? Isn't that to the right? Really to the right over here? There's your test statistic. What neighborhood is that in? You reject the what? You're rejecting the null because your test statistic is past the critical value of 2.36. So, reject your null. You go, okay, what is the null anyway? It's right here, rho equals 0, no linear correlation. Rejecting the null means accepting the alternate. What's the alternate hypothesis always? You have a linear correlation. This is why we say there's a linear correlation between the two variables. You're done. You're really done. You're done by the traditional method. Is that right? Aren't you done by that? Once you get your test statistic, you have your conclusion. Now, let's pay attention to these other values, right? You say, what does this mean, by the way? Isn't this a p-value? But be careful. What do you guys know about the p-value? E to the minus 7 power. What's the story there? That's approximately what? No, I don't think I put it here. What's happening to my notes? P-value is approximately, I guess I'll put it here. It's approximately 0 again. Isn't that less than the 5%? And if that's the case, you automatically accept the what? Alternate. Remember that p-value method? The modern method? And by the decision rule, that's exactly what we did. We accepted the claim, which is that there is a linear correlation. So everything should be coming together. If you're up to date with what you're doing, you're going, okay, I see the new template format, two-tailed test. Okay, that p-value modern method is about right. Okay, I understand. What is kind of new is that R value. Now, notice how close R is to 1. Isn't that that's like 99 cents, close to $1. So R is very close to 1. That's how strong this correlation is. It's a very strong linear correlation because it's so close to 1. Okay, so I want you guys to know that. I don't know if did I put it? Yeah, see this here? It's very close to 1, and it's positive. So we say this is a strong positive linear correlation because the R value is very close to 1. That's the meaning of that R value. So, you know, all of that information is working together for us. And again, once you know there's a linear correlation, what do you care about? You care about the A and B values, don't you? Because what do you guys want with those A and B values right in here? You want the regression line. So you could be predictive. Okay, regression line. What do we do? You know, how do I get that? Right? Over here. Y is A plus BX. Is that right? Okay. I don't know if it'll fit here. Maybe we got to put it down here. I don't know. I guess I'll put it up here. Y, what's the A value? If we go to the nearest thousandths, isn't that 5.10 Now B is also positive. 1.983x. Because here's my A value. Here's my B value. Do you guys see that there? This is called the what? What is this called? Once we find there's a strong linear correlation? That's your best fit line. That's a linear regression line. What do you care about that line for anyway? Why do you care about that line anyway? Because if there is a linear correlation, I can be predictive. I can now say, let X, we'll use pink, pretty in pink. If X is 11, there you go. Plug in 11 for X, you can now find the Y value. So you're going to enter here in pink, X is 11. What do you think you guys get here? Right? What's that Y value now if I put color it blue? It's 26.921. So we don't know what it means because it's general. You just plugged in that value of X in the calculator there. And here's what you got. What do you guys think? Easy peasy lemon squeezy? You just have to keep trying more and more examples. Now, anybody have any questions on this at this point? Because we're going to try more examples, and you can see how this goes. But I guess I have to give you a break. You guys ready for a break? Should I give you guys a quick break? You want to do one more example, or do you want to do a break? Another example or a break? I could keep going. All right. One more. Good. Okay. Saying I'm not ready for a break, Mr. Judge. Oh, here's the study time in the grade. Oh, it's perfect. Perfect. Remember, I got to send every class a reminder that you are out of time. So if you're busy doing on past homework, trying to sneak that in, aren't you out of time? How are you going to find the time to do today's homework, right? The current homework, if you're busy doing the past homework. This is why there's deadlines. This is why there's no late anything deadlines, because what happens is people, they go at their own pace. So if you're still working on test 1 or test 2 work, we're already where? We're way past that, past the deadlines. This is why you have deadlines. This is why you have to remind people, guess what? You got a study guide, work on that, work on what your homework 5 is now, make sure you meet your deadlines, because if you're not meeting them and you run out of time, there's no extensions. It's done. It's over. Once that door closes in the semester, it's bye-bye time. You guys know that? Because that's what people have to learn. I guess some people don't understand it. So remember, this is important. Study time and grade. Oh, I should have started with this one today. Darn it. What does it say? Bivariate sample data below are the study times in minutes and the grades in percent earned on an exam of randomly selected grades. Use the 5%. There's my alpha. Remember, they like 5%. Alpha, 5%. Low significance. Oh, I'm going to write that down. To test the claim that there is a linear correlation between the time studied and the grade earned on exam. What do you guys think? Does that kind of sound like there possibly is a linear correlation? Or is it random? What are they saying? This is all the bivariate data. Study time in minutes. If someone put 20 minutes in, what grade did they get as a percent? That's 40%. Okay. If somebody put what? 40 minutes in, what grade? 45%. Let's say you put 50 minutes in, your grade is what? 70%. Let's say you put 60 minutes in, your grade is what? 76%. Let's say you put 80 minutes in, what's your grade? 92%. You put 100 minutes in, what was the grade? 95%, ladies and gentlemen. This is the bivariate data. How many data values do we have here? We have what? 1, 2, 3, 4, 5, and what? 6. 6 data values? Okay. My degree of freedom is what? 6 minus 2. Isn't 6 minus 2 4? And there's your alpha, 5%. So, ladies and gentlemen, you might say, how in the world did they give us these what? Well, critical values. Well, we'll see. But first, we got to do what? We got to do a scatter plot, don't we? We got to enter the data and do a scatter plot. We want to see if we should proceed with a hypothesis test. So let's enter this data. What if the scatter plot is random? All right. How do you enter data? Stat, edit, edit. Clear out list 2, go up, hit clear. Go up, hit clear. Enter your data now. So in list 1, what do we do? 20, enter. 40, enter. 50, enter. 60, enter. 80, enter. 100, enter. There's my data. Now, list 2, we're going to put what? 40, enter. 45, enter. 70, enter. You're entering your data, ladies and gentlemen, bivariate, 2 variables. 76, 92, 95. There's your data, ladies and gentlemen. Didn't we enter that information? Okay, so we want to create a scatter plot. Do you guys remember how to do that? What do? Second Y goes, there's my stat plot. Make sure it's on plot 1. You hit enter. Make sure you have it on. It is. Make sure it's on. That's a scatter plot, by the way, the first one. Now what do you guys hit? Do you guys remember what you hit? You hit zoom. And you scroll down to zoom stat. Does that look like the data fits on a straight line, kind of? I would say what? Yes. It may not be as strong as the other example. The other example, the data looked like it's really on a line. Well, this might be a weak. This might be a weak positive correlation. Weak positive correlation. Okay. So now that I know it's a weak positive correlation, right, I'm going to try to set up my what? My formal hypothesis test. So I need my critical values. So if you remember how we got these critical values, just to review how you get that, what do? You have to use inverse what again? Don't you use inverse T? So we go second distribution, inverse T, and I think I have to clear that out. Okay. Second distribution, inverse T. There we go. It's still 0.975 because it's still 5%, 2 tails. But what's my degree of freedom now? Wasn't it 4? I think it was 4. 6 minus 2? Hit paste. You get 2.776. Is that right? Well, that's exactly what I put here for you guys. So what I have here is all the summary. So I'm going through these examples here of what you would do. Now, remember, what do we do now? We want to go to what? To get all the information we need, we have to go to stat, test. What do? There it is. Linear regression t-test. Okay, make sure it's on now 1 and now 2. It is. Two-tailed test. It is. Now hit what? Calculate. Again, this is all the values we need. Let's read it. Let's read it here. So if I have to fill in this information now, I need all this RTP conclusion, best fit line. Let's get this information. You guys ready? See if you guys learned something here. What's your test statistic to the nearest thousands here? Anybody know? Can you see that here in your calculator? What's the test statistic? 6 point what? 0, 9 what? 0. Is that true? You guys get the test statistics? 6.090 in the calculator? What does that mean? Where is that? Isn't that to the right? 6.090, isn't that where your test statistic is? What neighborhood is that in? Can you guys see it? Your test statistic is in the reject the null neighborhood. What does it mean to reject that null? It means you accept the alternate. And the alternate is the claim, which is there is a linear correlation. This is your conclusion, ladies and gentlemen. You're concluding there is a linear correlation between the two. So I want you guys to know there's a conclusion. There is a what? A linear correlation. So you guys know you're writing that down. If they want the p-value, go back to the, what's the p-value here? Do you guys know? Remember, p-value, we're gonna go to the nearest what? Hundredths. What's your p-value? Approximated to the hundredths. Do you guys know? You're looking at it. Isn't that the, you see what the p is? What's that going to be? 0.00? All right. Now, is that number, the p-value, smaller than the level of significance? Is being broke smaller than having a nickel? Remember that? That's what we check. What does that mean? You automatically accept the alternate hypothesis when you satisfy that by the p-value method, the modern method. So we did automatically accept the alternate. So it's verified. So I want you guys to remind you guys, you had the modern method and the traditional method and the modern method. This is kind of review. Is that true? So I just want you guys to see that. What's next? What is the R value? Oh, the R value, we have to scroll how? Down. What is that going to be? R is going to be what? 0.90. What is R? It's not 90. It's 9 what? 95 what? I think that's 950. Do you guys see it? The last line, R? There's an R there? All right. What's interesting about R? R is close to what? Isn't that close to +1? What does it mean if R is close to 1? Strong what? Positive linear correlation. So when R is close to 1, strong positive linear correlation. There you go, ladies and gentlemen. So now you know it satisfies all the linear correlation information. What do we need here? We need the best fit line. Is that right? So y equals what? A plus bx. Do you guys know what A is approximately here? What is A? 24.85 what? 7. What is B? Do you guys know what B is? 0.76. Is that 8? If we go to the nearest thousandths. Okay. So it has everything you need, even the A and B value here. So this here is the what? The best fit line, also called the regression line. What do you guys think? Is that an easy process? Okay, so what do they ask us? I think that's all they ask for. Anyway, that's all they asked. Here's the information they're asking for. Should we take a break or should we do another example? Keep going. Okay, I'll give you guys a quick break. Let's get the clock. All right. Go to McDonald's. Okay, quick break. And we'll continue because, like I said, this is, it gets easier the more and more you do. Okay. All right, folks, here we go. Let's try it again. Here's an example where they have what? Customer service and computer sales. All right, so what does this say for us? The bivariate sample data below are the number of customer service calls per week and the computer sales in thousands at a computer wholesale store. Now, use the 1% level of significance to test the claim that there is a linear correlation between the number of calls per week and the computer sales in thousands. So this is why they call you all the time, ladies and gentlemen. So, number of calls per week. When there's 10 calls, what's the story? They made $37,000. Okay? This is the X value. This is the Y value. When there's 15 calls, how much was made? $43,000. 12 calls, how much? $37,000. 20 calls, how much? $49,000. 25 calls, how much did they have in computer sales? $54,000. When there's 17 calls, how much? $45,000. Now let's take a look. How many data values were gathered? 1, 2, 3, 4, 5, and 6. So my degree of freedom, 6 minus 2, which is 4. Okay. And alpha is 1%. So this is why your degree of freedom is 4. And your alpha is 1%. And this is, we're going to show you how you get critical values for that test. But first we got to do the what? The scatter plot. But we got to enter our data. So let's enter the data now. So we go to stat edit. Stat edit edit. Now clear this out. Go down, go up, hit clear. All right, let's get the data values, right? You guys ready for the data? So 10, enter. 15, enter. 12, enter. 20, enter. 25, enter. 17, enter. Okay? So that's the first. Now go to L2, right? And you're going to hit what? 37, 43, 37, 49, 54, 45. All right. So you just entered your bivariate data. We want to check to see if this data, when we create a scatter plot, is in the form of a line now. So remember how that's done here. Second stat plot. It's on 1. We're going to hit enter. Make sure that's on. It is. Make sure it's on scatter plot. That's the scatter plot. X is L1, Y is L2. Looks like we're good to go. Now, hit what? Zoom and go down to zoom stat. It's kind of a weird procedure. Anyway, what do you guys think about that data? Does that look like it's in the form of a line? What do you guys think? Isn't that in the form of a line? That looks pretty good to me. That's, again, positive. Looks like it's going to be strong because it's almost exactly on a line. So, okay, looks like we're good. All right, now, so ladies and gentlemen, you go to your default hypothesis testing here. So rho H naught is rho equals 0, no linear correlation. H1 is rho is not 0, there is a linear correlation. It's your claim. Now, you might say, Mr. Judge, how in the world did they get our critical values the way they did? Well, this is half of alpha, half of alpha. Remember this. This is 99% now. So area to the left for inverse t, you're going to take 99%, the half a percent, that's 99.5%. Area to the left of the rightmost critical value. This is how this calculator does it. What was our degree of freedom again? Right? Is 4. So in order to get those critical values, we're going to have to use, again, the distribution here is that t-test. So you got to use inverse t. So in inverse t in the calculator again, second distribution, inverse t. Oh, I hate when it does that. I don't want to do the clear. Second distribution, inverse t, 0.995 for the area because alpha is 1%. Oh, it's still on the degree of freedom of 4, which is good. So notice we get the critical values of 4.604 to the nearest thousandths, by the way. And that's exactly what we have here in the sheet. So I want to share with you guys all the gory detail in how to get critical values because we use inverse what now? T. All right, there you guys go. It's always a two-tailed test. You're doing the default setup here for this. That's your decision rule. Okay, all the notes in the video there. All right. So I'm going to get rid of this because I don't want to be distracted, but it's in the video. It's in your notes. Now, we're going to do the linear regression t-test to get all the information we need. Linear regression t-test. Anyway. So, okay. Stat test. Go down to linear regression t-test. There it is. It's F. Make sure it's on L1 and L2. It is, and it's on a two-tailed test. It is. All right, hit calculate. So now I get, remember, all of this information is what I'm seeking. Okay, so if you can read this, tell me what is the test statistic? What's it going to be? Go to the nearest thousands again. Test statistic is what? 14.020, ladies and gentlemen. Is that true? So here's the test statistic value. This is what they want. We got to see where this lives in our decision rule, right? So 14 is where? Wow, 14 is really way what? Over here. 14 point, what was that? 020. You reject the null hypothesis. So when we reject the null, what is that? Rejecting the null means you accept the alternate. So there is a linear correlation. So you're done with the conclusion by the traditional method. The conclusion is there is a what? You do have a linear correlation. I'm trying to get red. Okay, by the modern method, by the p-value method now, right? So we're going to get all these values. So what is your p-value approximated to the nearest hundreds? Be careful here, because what you should see is that there's scientific notation. This is 1.5 times 10 to the minus 4. There's 3 zeros. So ladies and gentlemen, this is approximately 0. So what that means is, remember this, when the p-value is smaller than the level of significance, it's 1% level of significance. There's your p-value, which is true. Being broke is less than a penny. You automatically accept the what? Alternate hypothesis by the p-value method. So accepting the alternate here, that's the H1. There is a linear correlation, which verifies what we got by the traditional method and your decision rule right in here. So ladies and gentlemen, there's an example where alpha is 1%. Okay. Oh, how strong is this? What's the R value? What's the strength of the linear correlation now? R. Well, we have to go back to the calculator again. And we have to scroll down because what's the deal? R is at the bottom there. It's the last one. So what is R approximately again now? R is going to be what? 0.9899. That means 990 to the nearest thousands here. Your R value. So ladies and gentlemen, this is close to 1. It's close to positive 1, which means your linear correlation is a what? There's a strong positive linear correlation. This is why you're looking at the R value. It's a strong positive linear correlation. It's very close to 1. If it's not close to 1, well then, there's a linear correlation, you say it's a weak linear correlation. If it's close to -1, then it's a strong negative. If it's not so close to -1, but a linear correlation, it's a weak negative. But since you have a linear correlation, they're going to always ask for the what? The best fit line. Your best fit line is the equation y equals bx. This is also called the regression line. Okay? Because there is a linear correlation. So regression line. Regress. Well, how do we get that? We need the A and B value and the TI. So I typically go to the thousands to get an accurate kind of representation. So A is 24 point what? 135, right? What's your B value? You guys see it? So the nearest thousands is 1.214x. Okay, so y equals A plus bx is this regression line. And that's what we have here. We can use this to be predictive again, if we wanted, For example, you said, what does this mean? Well, if you made how many calls per week? Let's say you did 28 calls or something. How much do you make if you made 28 calls in a week? How much did you make in thousands of dollars? So I'm making up this question, okay? So if X is 28, that's the number of calls. You plug in 28 in here, then y is going to be a number. What is the number? $24.135 plus 1.214 times the number 28. So I'm going to go to the nearest thousands to approximate, ladies and gentlemen, because it looks like the y value was to the nearest thousands. What they're saying here is that if x is 28, y is going to be 58,000. So if you make 28 calls, that's the number of calls per week, you can expect to make $58,000 with this model. Because there is a linear correlation here, ladies and gentlemen, for the number of calls and how much you make. This is why they call you all the time. This is why they bug you with calls, because there's a linear correlation between the number of calls and how much money they make. What do you guys think? Is that okay? Has it gotten easier? What do you guys think? Is this stuff easier or is it harder? I don't know. How many examples do you guys think you have to do? I don't know. Let's see. What do you guys think about this? Police officers and muggings. I don't know. Let's see if there's a linear correlation here between police officers and muggings. What are they talking about? Okay. The bivariate sample data below is a sample of the number of police officers on patrol in a small city and the number of muggings in the same city. Okay. Use the 1% level of significance to test the claim. The claim is there's a linear correlation. There is one between the number of police officers on patrol and the number of muggings. So what do you think they're kind of talking about, right? What do you guys think they're saying? When 20 police officers are on patrol, there were how many muggings? 8. When 12 were on patrol, how many muggings? 10. 18 were on patrol, how many muggings? 12. 15 were on patrol, how many muggings? 9. 22 were on patrol, how many muggings? 6. And so on. You guys see what I'm saying? So remember what you want to do first. Before you try to do anything, create your scatter plot. But you got to enter the data in. So we're going to enter this data. All right, let's do that here. Let's enter data here, okay? Enter data. So, okay, go to the TI now. Remember that. Stat, edit, edit. Clear this out. All right, let's enter the data. 20, enter. 12, enter. 18, enter. 15, enter. 22, enter. 10, enter. 20, enter. 12, enter. Okay, the next is 8, 10, 12, 9, 6, 15, 7, and 18. So double check. Do we enter our data okay? Does it look like we did it okay? All right. Scatter plot now. You go, what do I do for scatter plot? Second scatter plot. Yes, it's on number 1. That's what we're looking for. Stat plot's number 1. Make sure this is on, and make sure you're on the first one, scatter plot. L1 and L2, pretty much it's there. So everything's good. All right. Zoom, and then what? Zoom stat. Oh, what does that look like to you? Ladies and gentlemen, I'm not so sure that data can fit on a straight line. What do you guys think? If it does, I don't know. I don't know if we can fit that data. If it does, it's a weak negative line. It looks kind of randomish to me. It's possible, but I really don't know for sure. Okay, so what I'm going to do now here is this for you guys here. Let's go back here. Since this is supposed to be 1%, I'm going to say that here right now, 1%. So 1%, I think I'm going to go back again. Let's use, okay, it's 1%, I guess. Whatever. How many data values? 1, 2, 3, 4, 5, 6, 7, 8. Let's see. How did I do this here? No, I did 5%. So I apologize here. Okay. So in the picture, I did 5%. So we're going to say get rid of this 1%. Change this to what? 5%. So I'm using the 5% level of significance. Sample size is 8. My degree of freedom is 6. So we're going to get the critical values by using inverse T. So it'd be plus or minus 2.447. Okay? So remember how that was done, because this is 95%. Area to the left of the rightmost critical value. So that'll be 97.5% area, with our degree of freedom to be 6. Right? So remember, set up your hypothesis this way with H naught is rho equals 0, H1 is rho not 0. That's the claim. That's the template. Let's use inverse T to see if this is correct. Maybe there's another typo. I got to go work some more. Second distribution, inverse T. I'm going to clear it out. Second distribution, inverse T, 0.975. Now here, what is this? 6. Paste that in. Sure enough, isn't that exactly what I have here in the notes here for you guys here on this? Okay, this is how we got the critical values now. We have to use inverse T because this is a T distribution. Okay. So, all right. All right. Let's now find out here. Since we have our hypothesis set up, we have our decision rule. What are we going to do next? You guys know we got to use linear regression t-test. That's in the TI. Sorry about that. Okay. So we're going to say what here? This is stat test linear regression t-test. Go all the way down to that, F. Make sure it's on L1 and L2, two-tailed test, right? Looks good. L1, L2 for the X variable and Y variable, two-tailed test. Hit calculate, ladies and gentlemen. All right, where is your test statistic value? It's in purple. Well, it's not in purple yet, but we'll put it in purple. What's the test statistic? Isn't that negative 3.07? What is it? Negative 3 point what? 073. Okay. What do we know? Where is that? Let's get rid of the distraction. Where is this number at, right? Negative 3.073. Where does it live on the decision rule? Isn't that to the left here? It's to the left. What region is this in? We're going to reject the null. So if we reject the null, what does it mean about the alternate? What's the conclusion? Conclusion is that there is a what? A linear correlation. Let's see what the p-value says, right? The p-value, let's see that p-value since they're asking for it. Your p-value is about 2 pennies, right? If we go to the nearest hundredths, isn't that about 2 pennies? What was that level of significance? Wasn't that 5%? Okay. So 2 pennies is smaller than a nickel. Don't we have to accept what? The null automatically by the p-value method? So if 2 pennies is smaller than a nickel, we have to, what do? We accept the null. And that's exactly what we did when we rejected the alternate by the traditional method. So ladies and gentlemen, this is the deal here for you. Okay, there it is. So we are just verifying the two methods, just as a review. Now, all right, now you say, what's the R value? Sample linear correlation coefficient. And notice what I'm saying here about the R value. I want you guys can see this here. R is approximately negative, 0.782. Okay, this is what I want you guys to remember about this R value. R is really not close to what? It's not so close to -1, is it? It's not like -999 or negative 0.999 or negative 0.95. So even though there's a linear correlation, what this says, you have a weak what? Negative. So there might be a linear correlation, but you want to know something. It is what? It's weak. So the R value has a lot of good information. It's not so close to -1. Okay, you guys see what I'm saying? Not close to -1. There's still a linear correlation, but it's not very close. Yeah, go back to the calculator. Well, before we do that, let's do this. Let's get the best fit line. Do you guys remember the best fit line? What's the definition? Y is A plus BX. Remember that? What's your A value here? What's A? 22.257. What is B? That's minus point what? 721x. Do you guys see the A and B values there? We go to the thousands. A is 22.257. B is negative 0.721. So this is your, what is this? This is your what? This is a regression line. That's the best fit line. There it is. So they're going to want all this information from you guys. And so what I did start to say is, you know, this is a weak negative. That line has a negative slope. So if I go back to the calculator to what? See the scatter plot. I want you guys to remember this, that was in fact what? A weak scatter. It's a weak, you can't fit a lot of that data on a line, and notice the line is kind of a negative, it's a negative slope there. You know, that's kind of how this data is. So it is, there is a weak linear correlation. It's not strong. There is one. And I just want to go back and share that with you guys. And anyway, nevertheless, ladies and gentlemen, if I find the video, I think there's weeks in weight loss, whatever. Ages and miles you run, maybe pizza and Subway. So if I can go back and find them, I think I will. I'll try. I can send you guys examples that other classes have done with this. If that's what you guys want to see, I can send that to you. But I also did what here? Let's go to Canvas here. Let's go to the website. Oh, ages and miles run. No. You know what I like? This very famous one. Pizza and Subway fare. Pizza and do you guys know? This is in New York. This is a very famous question. That this bivariate sample data below represents the cost of a slice of pizza and the price of Subway fare in New York City. Very famous question. They're going to want you to use the what? 1% level of significance to test the what? Test the claim that there is a linear correlation between the two quantities. Do you guys know that people have looked at this, believe it or not? You think it's silly, but you go, wait a minute. The cost of a pizza slice and the Subway fare, there's a linear correlation? Oh, let's take a look. Do you guys see? This is the sample of data. In other words, in 1960, pizza cost 15 cents. What's the Subway fare? 15 cents. Interesting. Sorry, I want to change that to green. In 1973, what happened? 35 cents. What's the Subway fare? 35 cents. 1986, pizza cost $1 for a slice in New York. You want to know how much Subway fare was? 1. So what I'm saying to you guys is people have looked at whether there's a linear correlation between the cost of a slice of pizza and that of Subway fare. There's going to be what variable here? This is going to be what? X, and this is Y. Now, with the we're gonna enter that in our TI, okay? Let's do that here. We don't have a lot of time, but let's do that one. Stat, edit. Okay, I'm gonna have to clear. Okay, let's enter this information. 15 cents, enter. 35 cents, enter. $1, enter. $1.25. Enter. $1 what? 75. Enter. $2. $2 and what? 25 cents. Okay, $2. What's the next one? 125, 175, 225, and then what? $2.30, and then $2.75. Okay, so you entered the cost of a slice of pizza. Now we're going to enter what? The 15 cents here. 15 cents, 35 cents, $1, $1.35, $1.50, $2, $2.25, $2.50, $2.75. Okay, so you got your bivariate data. Now what do you guys do? Got to look at scatter plot. Second stat plot, it is on plot 1. Everything is as it should be. Zoom. Go down to zoom stat. Alrighty. What do you guys think? Does that data look like it fits on a straight line? Yeah, it looks pretty good to me. What do you guys think? That looks good. Anyway, so we're going to proceed. So as you proceed, to remind you guys, there was a sample size of what here? 1, 2, 3, 4, 5, 6, 7, 8, 9. What does that mean about your degree of freedom? 9 minus 2 is 7. Alpha, though, is what? 1% level of significance. So use inverse T. You know what you're going to get? Inverse T, you're going to get these critical values. So I'm going to let you guys double check. But notice the hypothesis setup is exactly the same. It's kind of like a template. It's the same. H0, rho is 0, no linear correlation. H1, rho is not 0. There is a linear correlation. It's a two-tailed test. You guys okay with that? Same setup. All right. Here's your decision rule. So what do we do now, ladies and gentlemen? Do you guys know what you do now? What was the command in TI? Linear regression t-test. Is that right? Have we seen enough of these where we know? Let's get the information now. All right, so here we go. Linear regression t-test. Stat, test, linear regression t-test. Isn't everything on L1, L2 not equal? So it looks like we're good. Is that right? Okay. So let's get our test statistic. Oh, didn't see it. Sorry, I have to do it again. Stat, test, linear regression t-test. Calculate. There we go. Let's zoom in. What's your test statistic, ladies and gentlemen, to the critical value, the nearest thousands? You guys know what the test statistic is going to be? What is it going to be? Tell me which one. Good job. 20.464. Do you guys see that? Good. All right. That's your test statistic. Good. Where does that live on the decision rule? Wow. What do you guys notice? That's really to the right of the critical value. Is that right? Is that really to the right? What's the neighborhood? Bless you. What's the neighborhood? You're going to reject the null. Reject the null. Here we go. Goodbye, null. If you reject the null, what do you guys accept? The alternate happens to be the claim. And what's the claim again? There is a linear correlation. So your conclusion is going to be that you have a what? a linear what? Correlation. There it is. Okay, what is the best fit line? I mean, you could verify if you guys wanted. You go, oh, Mr. Judge, what's P? What's R? Well, P, notice is this. P is extremely small because that's scientific notation again, right? Don't forget the e to the -7. That's really move the decimal 7 spaces to the left. So again, P is going to be what? 0. You go, oh, my p-value is 0. Yep. And notice the level of significance, that p-value will be less than alpha, right? So 0, 0 is less than the alpha being 1%. That means you automatically accept the null, which was exactly what we did here. We did that already. So the p-value method is verifying everything. How strong is that correlation now? What's the R value? Oops. TI, what's R? Well, we're going to have to scroll down. R is approximately what? 0.99 what? 1. Is that right? Or 992. You're right. 992. You guys know something about that number? That is pretty close to what? That's close to 1. That's even closer than the last one. So that's close to 1. So it's pretty strong. I would say that's a strong linear, strong positive because R is positive. If R is negative, it'd be a strong negative. You have a strong positive linear correlation. Good. How do we get the regression line so we can be predictive? You guys know A plus BX. So what's A here? You guys see what A is? Negative 0.011. Is that true? And then what is B? 1.01. Is that 0? That's 1. Is that right? So get your A and B values, ladies and gentlemen. A and B. And what do we call this? This is the what? The regression line, also known as the best fit line. So we could use that line to be predictive, so you guys know. So we went through some more examples. I will send some more to you, but let's take a look at what is happening, okay? So if I go to the assignment portion, let me go here. On homework number 5, you go, you're going to give me homework on this? You go, well, what is this? Let's take a look. Okay, so I want you guys to I hope you guys know there was a website because sometimes people ask that. See this worksheet? What? All right. Let me refresh this. Sorry. See this worksheet? That's homework on linear correlation and regression. You go, what? You're going to make me practice this? Well, why would I do something like that? Are these solutions? Yeah. Are you going to copy the solutions? I hope not. You're going to copy them and submit as your own work and say, here you go? People do. Notice there's no work when they send it. It's just my answers. I noticed that. And oh, okay. I see what's going on. I wasn't born yesterday. All righty. Okay, I see. But anyway, I have solutions here for the homework. And you might say, why would you make me do homework?